Hello everyone, I'm Ming Lu, former research fellow at University of Houston. Today I'm going to talk a little bit about the numerical method to predict the mechanical behavior of cross-linked polymers, working on the elevated temperatures, pressurized and chemically reactive environments. In our daily life, after long-term service or shelf storage, you will notice failure caused by degradation of elastomers on tiles, valves, or cooling systems. Such degradation may essentially lead to crack initiation or accelerate crack propagation. Even without cracks, elastomer components may not function at its original pressure rating, which is extremely dangerous in some scenarios. For instance, failure of packing elements in blowout preventer may result disaster in oil and gas production. Moreover, degradation of elastomers also change the function temperature range, which is closely related to the glass transition temperature of polymers, and therefore lead to unexpected failure on the temperatures well above their designed working temperatures. One of the most studied degradation mechanisms is thermo-oxidative degradation. Oxidants attack the cross-link sites, or backbones, which is described as chain stitching. Some researchers use FTIR to study thermo-oxidative degradation, based on change of relative ratio of peak height of chemically active functional groups to inactive groups, and therefore we can semi-quantitatively identify the progression of thermo-oxidative degradation. Besides the normal reaction conditions, there is also something most people will ignore. We will see triple phase point on water or carbon dioxide phase diagram, which is called supercritical point. Water will behave chemically reactive when approaching or beyond this point. For instance, nitrile rubber is mostly stable in water-based solutions. However, as in subcritical or supercritical water, it may not be the case. Free radical type reaction can happen, which no doubt should be taken into account in chemical-induced degradation. This is of critical importance as we design elastomer components that work on the harsh environment. Understanding the important factors in degradation, we plan to develop a model to better understand the long-term degradation of elastomers. First of all, we have to address the diffusion problem of small molecules inside cross-linked polymers. Here we refer to the free volume theory, developed by Vrentas and Duda. In this theory, volume of molecules themselves are called occupied volume. The space occupied due to thermal vibration of large molecules is called interstitial free volume. And the rest, which is the only free volume available for diffusant migration, is called whole free volume. Considering the motion ability of large molecules, whole free volume is more sensitive to temperature change than occupied volume and the interstitial free volume. We will see how significant temperature will affect the diffusion in following slides. The equation developed from mass transfer is used to describe this process. However, diffusion coefficient of small molecules diffusion inside cross-linked polymers is no longer automatically considered as constant. It is basically a probability of diffusant jumping frequency from its original position to the neighboring free site. Obviously, with larger whole free volume in unit volume, we can expect a greater diffusion coefficient. I'm not gonna discuss in details about the diffusion coefficient in free volume theory here. By plugging in the modified diffusion coefficient and include the chemical reaction term, here we assume a first order reaction which is close to most cases we were dealing with. We will have the governing equation that describes the diffusion reaction process of small molecules in cross-linked polymers. And by solving this initial value problem, we can derive the history of diffusion profile within the bulk polymers. To derive the numerical solution to this problem, we'll have to discrete in spatial domain and time domain respectively. We approximate the real-time local diffusion rate and substitute in the governing equation. And the problem is reduced to a simpler form of PDE, and the numerical solution can be derived with finite difference method. So here we have the results after aging for selected time spans. First of all, we would like to check the temperature effect. We can see from the diffusion rate expression that with increased temperatures, diffusion will accelerate and diffusion accumulation can be observed in the diagram. However, reactions also strongly depend on the temperatures. There is competition between the accelerated ingression and the consumption of diffusant. Secondly, we examine the pressure effect. The major difference here is the solubility at the interface. Henry's law is used to derive the solubility and also boundary conditions. Higher pressure leads to higher solubility at the interface and in sequence affects the diffusant profile. For chemical kinetics, we can see that diffusant will immediately used up with faster reaction rate, and no accumulation is observed inside the cross-linked polymers. Obviously, this is based on the availability of reaction sites in cross-linked polymers. We can also see that the difference between the Fickian diffusion on the standard temperature and the pressure from diffusion reaction process on the subcritical condition. Chemical reactivity under certain high temperature, high pressure conditions makes the difference and cannot be neglected. Lastly, we try to see how cross-link breakdown affects the diffusion reaction process. And we find that the influence is very limited compared to other factors. To link the diffusion reaction solution to the mechanical property of elastomer, we need to apply the fine network theory, which is used to describe the elasticity of elastomers in the view of statistical thermodynamics. In a fine network theory, free energy change is calculated. For commonly used rubber categories, Poisson's ratio is close to 0.5, and therefore volume change during deformation can be neglected, and so is the internal energy change. Mechanical performance of elastomer is most related to the number of interconnected chains in unit volume here. To get closer to the real case in cross-linked polymers, Flory has developed a loose end correction to describe the influence from chains not connected to the network. In our case, any types of reactions related to chain scission will generate imperfection which is similar to the loose end. Due to the undetermined reaction mechanisms, we are not going to treat them in details in this study. Instead, we introduce a parameter called transition efficiency to include the chemical, thermal, and crosslink formation breakdown effects. And we also notice that transition happening at the crosslink sites or backbones will have different efficiencies in transition. As a result, only effective transition is meaningful in this model. This parameter represents the frequency of effective transitions taking place in unit volume, unit reactant concentration, per unit time, under certain temperature. We substitute the integration of effective transition efficiency over time in the loose end correction to the elasticity of an elastomer, and got the expression of degradation on mechanical properties of elastomer after aging. By counting the consumption of diffusant over time and correlating it to the damage on the network of cross-linked polymers, we are able to quantify the total effective transitions happened. With aid of FEA, we can subsequently predict local mechanical properties after long-term aging. By partitioning and integration over the bulk polymer, we will be able to predict the long-term mechanical behavior of our elastomer components working under high temperature, high pressure, and chemically reactive environment at the design stage. To validate the modeling and also study other mechanical behaviors of polymer materials under high temperature, high pressure, and chemically reactive environment, we built a high pressure rating reactor connecting directly to our mechanical test frame, which is capable to perform in situ mechanical testing. The basic idea is to seal the samples and the chemical fluids in the chamber and make the sample ready to be tested before aging. Inner gas is regulated to build pressure inside the chamber. With this setup, we no longer need to take out samples from reactor and mount them on the test grips after aging. This setup not only can simulate the real work condition, but it eliminates the annealing effect during the transfer of polymer samples from reactor to instrument machine. We built two prototypes. The very first version works under 2 megapascal and use expansion joint as the motion part. And the most recent version is improved to be able to work under 10 megapascal. We use the first setup to study stress realization behavior of HNBr materials under high temperature, high pressure, and chemical reactive conditions. You are welcome to refer to our paper, which is provided in this slide, for more details. In this study, we summarize the research on small molecules ingression in the cross-linked polymers and developed a numerical method to quantitatively predict the mechanical behavior during and after aging. We are working on experimental investigation to validate and improve our model, and also trying to introduce the effect of polymer disintegration from the bulk polymer and extend our research to more polymer families. I would like to thank Schlumberger, Texas Center for Superconducting at the University of Houston, and the Suzhou Guren Nanotech for their funding support and assistance in experimental study. Thank you for joining, and please do not hesitate to let me know if you have any questions.